In this video, we're going to talk about strong acids and weak acids, and we'll also talk about strong bases and weak bases. All right. So first of all, everyone here has probably heard of the phrase "strong drink." All right, and so what you might think is implied by strong acid is just simply a solution that contains a lot of acid, in the same way that a strong drink is simply something that's got a lot of alcohol or a high concentration of alcohol. However, when you're talking about a strong acid, it has a different meaning. All right. So strong acids are acids that completely dissociate in water when you dissolve them in water. In contrast, a weak acid is an acid that only partially dissociates. All right. So first of all, to describe this, we're going to have to use the generic Bronsted-Lowry equations. All right. So there's two ways, again, you can represent it. Either if you represent it, the thing that gets produced as H3O plus or H plus aqueous. Again, these are essentially the same thing. So an example of if we gave a specific example, we could represent this specific example. If we take HCl and you dissolve it in water, you would end up getting H3O plus and Cl minus. If we're going to use this type of way of representing things, something like H3PO4, we'll give H plus H2PO4 minus. All right. When you notice that in the generic equation, they have this thing A minus. All right. And A is just a variable that is used for stands for the anion of the acid. All right. And remember, anion is a negative ion. So in any acid, if you were to think of it like an ionic compound where H is H plus, what is left would be a negatively charged atom or molecule. All right, like H plus, and then what's left is Cl minus. All right, so since it's going to be an anion, that's why they choose A as the variable for that. All right, so so that's going to be a variable, and as we said before, what you have once the acid donates its H plus is what we call the conjugate base. So to describe what they mean by completely dissociating, all right, let's again use the generic equation above. All right, here we have it, and let's consider what would happen, what you would have in an acid before you add it to water versus after you add it. All right, so let's say before you take some of this HCl and drop it into water. All right, by the way, HCl by itself is just a gas, but what you would have is 100% HA. All right, and you would have 0 of this and 0 of the A minus. And the reason is, for this reaction to occur, these two things have to have come in contact with each other. All right, and so before these things come in contact with each other, you don't have any of these things. That's technically incorrect, but and we'll explain that in a second. But the reason is they just haven't come in contact yet. But once you add it to the water, what's going to happen? Well, what it means to completely dissociate is every single one of these HAs is going to react with water to generate these. All right, so if you had 100 of these in the beginning, after it's in the water, you have none of those. All right, so essentially the only thing that you're going to have in the water are these things right here. So since all of these break apart, all right, which means this reaction goes 100% of the way, all you're going to have is H3O plus and A minus. You're really not going to have any substantial amount of HA in there. All right. So I want to point out that this is technically incorrect because there is some amount of H3O plus present in the water simply as a result of the self-ionization of water. Why don't we consider that in this part right here? Because when you're adding an acid to water, the amount of H3O plus that's going to get created from that is going to be so large compared to the amount of H3O that is normally present in just pure water, that it's so small that you can consider it negligible, which means like you can pretty much pretend that it's not there. So some examples of the types of acids that would do this and therefore be considered strong acids. HCl aqueous. All right, notice I put aqueous after this. All right, that's what we call hydrochloric acid. All right, the reason that it's important that you put aqueous after this is it's also possible to get HCl as a pure gas where it's not dissolved in water. All right, and whenever you have that, you would just call it hydrogen chloride. All right. Also, you could get HCl dissolved in ether, and if you ever get HCl as a solution in ether, you also just call it hydrogen chloride. All right. Hydrochloric acid is specifically HCl dissolved in water. All right, because that's what's necessary for this reaction to occur. Another example would be H2SO4, which is sulfuric acid, and the last one is nitric acid. All right, so let's compare this to the example with a weak acid. So again, a weak acid is an acid where only some of it is going to break apart. All right, so again, what that means, let's pretend that you drop 100 units of HA into water. In the beginning, you have all HA and none of these things right here. And again, it's just because it hasn't contacted the water yet. But what are you going to have at the end? All right, well, what it means to partially dissociate is that some of the molecules break apart. So some of the molecules, like say 10% of the HA molecules will undergo this reaction, but 90% of them, they're just going to ignore the water and stay, like no reaction occurs. All right. Well, if that happens, what you have swimming around in the water is you get some H3O plus from the reaction that does occur. You get some A-, but you also have significant amounts of HA. All right, the undissociated acid. All right. And so that's what makes it a weak acid versus a strong acid, because in the strong acid, essentially you don't have any of the HA because all of the HA is broken apart. Okay, so one bit of vocabulary. Whenever you have a weak acid, the type of acid, the species where it does not break apart, generally you call that undissociated acid. The HA that does break apart to make the H3O plus and A-, you would call that the dissociated acid. So some examples of weak acids. We mentioned this one before, acetic acid. All right, again, there's several ways you can represent it. Sometimes it's represented like this to put that that acidic hydrogen, the one that gets donated at the beginning of the formula. I think it's more commonly shown like this. Structurally, this is what it would look like, and the hydrogen that ends up getting donated is actually this one right here. All right, if you remember from the little bit of organic chemistry, this is what's called a carboxylic acid. All right, and the reason that it's a carboxylic acid is that this acid can be donated to water. Another example would be H3PO4, that's phosphoric acid, and HF, which is hydrofluoric acid. All right, so keep in mind that strong versus weak does not mean the same as concentrated versus dilute. So just as an example, let's say that we had a lot of H2SO4 and we added it to water. All right, you would therefore have a concentrated strong acid. All right, concentrated because there's a lot of it. All right, strong because that just has to do with H2SO4. It is a strong acid. If you only added a couple of drops of H2SO4, you'd have a dilute strong acid. All right, which sounds kind of like a disagreement. Dilute only refers to, is there a lot in the water or is there a little in the water? Strong refers to when that stuff hits the water, does it fully break apart or does some of it stay connected and some of it break apart? All right, and we have these other examples here. If you added a lot of H2PO4, you would have a concentrated weak acid. You cannot make a strong acid by simply adding enough of a weak acid. All right, no matter how much you add, not all of it's going to break apart, and therefore it's not going to be considered a strong acid. All right, so what's the biggest difference that you would notice about a strong versus a weak acid? All right, so let's take a look at these two examples. If we added the same number of molecules of a strong acid to water, and over here we add that exact same number of weak acids to water. All right, notice that when you're done, you're going to end up creating more H3O plus molecules from the strong acid versus the weak acid. So the water that's had the strong acid added to it is going to end up having more H3O plus swimming around in it. All right, and remember, that's how we describe, that's what acidity is. Acidity is that ratio of H3O plus to O minus. All right, so recalling that pH is the negative log of H3O plus. All right, if you have more of this, you're going to have a higher number there. All right, and that's going to end up giving you a lower pH. All right, so if you had the same number of molecules of a strong versus a weak acid, the resulting solution is going to have a lower pH, meaning it's more acidic if you've added that strong acid. All right, so one of the first things that we could do is we could figure out what the pH of a solution containing a certain amount of a strong acid would be. All right, so as an example, let's start with a question. What would be the pH if you added 1.2 grams of HCl to 1.34 liters of water? All right, so the first thing what we want to do is write down the equation of HCl dissolving in water. All right, so that's what this would look like right here. And what we could assume is that this reaction is going to go all the way. All right, you're not going to have any of this anymore. We're going to have all of this. And the reason we can make this assumption is because this right here is a strong acid. All right, so we know that pH is the negative log of the hydronium ion concentration. So notice that right there is one of the things that gets created. All right, so if we can figure out what the concentration of this in the water is, we can figure out what the pH is. All right, so to solve this equation right here, what we need to do is figure out what the molarity of that H3O plus is. And molarity is always moles of whatever you're talking about divided by the number of liters of solution. All right, so if we look here, we've got the volume of the water. Actually, this should technically be the total volume of solution, because if you add something to a certain amount of water, it does change the volume a little bit. But in terms of how would we figure out the number of moles of HCl? Well, we could use a little stoichiometry here. We have an equation here, and we know that this equation goes all the way. So let's start our little crossbar with an amount of HCl. We can convert that to moles, and what this equation says is that for every 1 mole of HCl, we're going to generate 1 mole of H3O plus. All right, and notice that this right here, this assumption is something that we can only do because it's a strong acid. And if this was a weak acid, we can't do this, because for every one of these, we don't end up generating one of these, because not all of these end up generating that. You're just going to get a percentage of these that end up generating the H3O pluses. All right, so if we set this up, we would figure out that it's 0.0307. Notice we're paying attention to our sig fig rules here. And we're going to take that and we're going to divide it by the volume of the water, or of the solution. That gives us this right here, and just taking this number right here and plugging it into the pH equation would allow us to solve for the pH. Okay, we can also solve for the pH of a solution if we add a strong base to it. All right, so taking this taking this right here and adding it to this much of the solution. So we're going to first start by drawing this dissociation reaction. And you'll see that if we have one of these, we're going to get 1 sodium and 1 OH minus. Remember, sodium hydroxide is an ionic compound, so that it would freely dissolve. What this allows us to do is figure out the concentration of OH minus. All right. So again, we're going to use a little bit of stoichiometry, and we're going to assume that for every one that we add here, it's going to completely break apart. So we can concentrate the number of moles of OH minus. Therefore, we can calculate the molarity, which is going to be 0.104. And what that allows us to do is to calculate the pOH. All right, so we can just take the negative log of that, and we would get this. All right, and we know that the pH plus the pOH equal 14. So once we have this, we can calculate the pH from that.